So now everything in this expression is squared. So we can take the square root out and write that beta is the ratio of p pi prime c over e pi primed. So that's kind of an interesting result. If you have a particle and you know it's the magnitude of its momentum, which in this case is p pi primed. Remember, we're in the primed frame just to remind ourselves that in this frame the pion is actually moving before it decays. So if you know the magnitude, the momentum of the pion and its total energy, there's a simple expression for beta, the velocity of the ratio of the velocity of the particle, the pion, to the speed of light. And notice this makes sense because for a massless particle, like a photon, the momentum times c is the energy, in which case the numerator and the denominator are the same and beta's 1. In other words, it's moving at the speed of light. So if you have a massless particle, beta tends to 1. If the particle's massive, then p prime c, or whatever the momentum is times c, is always less than the energy. So beta is capped, it's limited to be less than 1. In other words, particles moving at less than the speed of light. So everything works out beautifully. We can now use this expression for beta to derive an expression for the maximum energy of the photon. So if you remember, we've got the formula up here for the maximum energy of the photon. Okay? And so we know that gamma, now let's just write everything out. And so we've got, if beta's this, then 1 plus beta equals 1 plus p pi prime c upon e pi primed, which equals e pi primed plus p pi prime c all over e pi primed. Okay? And so now we substitute the 1 plus beta from this expression into the expression for e gamma primed. Okay? And so we end up with this expression. We have e gamma primed equals gamma. What's gamma? It's e pi primed over m pi c squared, and there's nothing there we don't know. 1 plus beta is equal to, this here is gamma, 1 plus beta equals e pi primed plus p pi prime c all over e pi primed. And e gamma is m pi c squared upon 2, because if you remember, the gamma rays share the energy of the initial pi meson, which in the unprimed frame, this is e gamma in the unprimed frame, the pi meson's at rest. So its total energy available is just m pi c squared. Now, you might think it's torture going through and doing this entire calculation with algebra, but now you can see the power of the whole thing. The power is that this algebraic expression contains an awful lot of cancellation. You can immediately cancel the e pi primed and the m pi c squared, and so you're left with a simple expression for the energy of the gamma ray in the primed frame. E gamma primed equals the sum of the energy of the pi meson in the primed frame plus p pi primed c divided by 2. Stunningly simple expression. Let's go on and apply that. Hello again. So finally it's time to stick some numbers back in. I'm going to erase a lot of this stuff now. You don't need it anymore. Right. So we have E gamma prime, which remember is the maximum energy the photon can have in the frame where the pi meson's moving. That is, it's the energy that they've measured for the photon when it's emitted in the opposite direction to the motion of the pi meson before the decay. So it's in the opposite direction to the direction of the observer travelling towards the pi meson as it decays. That's a better way of saying it. Okay, so for the energy of the pi meson E pi prime, we put 1000 MeV, right? The momentum P prime C we've already calculated. If you remember, that was 991 MeV divided by 2, and so you get E gamma primed equals maximum possible photon energy is 995.5 MeV. Notice that's almost all the energy in the collision. There's very little left for the other photons. So if you're moving directly towards the pi meson as it decays, and one of the photons from the pi meson happens to be emitted directly towards you, it's coming directly towards you, that particular photon is going to have most of the energy, and the other photon is going to have almost none. Now, I asked you in the question to get the wavelength. I do apologise, by the way, this question turns out to be a couple of years old and there was a mistake in it. I sent you an email before Christmas pointing out that the statement that the wavelength of each photon in the rest frame of the pi meson is 2.51 femtometers is actually a false statement and that you should ignore it. So I hope you're all paying attention to your emails and ignored that sentence. Before we get to the end of this lecture, we'll figure out what the wavelengths of the pi mesons actually are in this question, the maximum and minimum wavelengths. But let's just figure out what this energy converts to in terms of a wavelength. And I'm going to use a sort of trick to do this. So the wavelength, now because this is the maximum energy photon, it's going to be the minimum wavelength because big energies correspond to small wavelengths. And that's going to be Planck's constant divided by the momentum of the photon. Well, let's rewrite this as 2 pi h bar c over pc. So all I've done is introduce a 2 pi and compensated by making it h bar, where h bar is just h over 2 pi, and then introduced a c top and bottom. And then this pc I write as the square root of e squared minus m c squared all squared. This is for the photon, so of course in the case of a photon you can ignore this term because its mass is 0, because the rest mass of a photon is 0, and on the top we have 2 pi times h bar c. Why I've chosen to use these funny units, well you may remember it from lectures or you may not, I'll tell you in a minute. Okay, so the expression we end up with for the minimum wavelength equals 2 pi h bar c over E gamma, because the mass term goes away and the square root of E squared is just E. And we've got E gamma. It's 995.5 MeV. This is E gamma primed, of course, because we're in the frame where the pi meson is moving. And so you get 2 pi. Now the interesting thing about h bar c is it's 0.2 GeV femtometers. It's worth knowing that. H bar c in these funny units, 0.2 GeV times femtometers. And the reason that's useful is because you avoid having to calculate wavelengths in meters. As we'll discover, the number of meters in this wavelength is tiny. And then we divide that by our energy, which is 995.5 MeV. And you get a wavelength of 1.24 femtometers. So that's 1.24 times 10 to the minus 15 meters. Of course, you could do that calculation just using the momentum in kilogram meters per second, and Planck's constant is 6.67 times 10 to the minus 34 joule seconds, and convert the momentum and calculate everything out. If you got the right answer, that's fine. The trouble is that it's easy to make a mistake in doing all the unit conversions, so I recommend not doing that. So next we'll go out and figure out the energy of the other gamma and what's happening with the physics there.